right, welcome back, everybody. Today we're covering recursion. This is chapter 2. I opened it up. You still got plenty. The first test is like October 6th. If you're falling behind a little bit, you still got plenty of time. Some of us are fucking overachievers and like to be done like with homework super duper quick. Like I think he submits it before I finish fucking lecturing on it. Mitesh, that's you. Fucking always on time. All right, so recursion. Let's take a look at recursion. I've copied and pasted this into my shit. Let's see. Move stuff out of the way. So we're over here, and before we do it, let's just talk about what recursion is. Recursive functions are functions that call themselves. Which means they need a terminant, something that terminates the call. And this is called the base case. So as it's going through it, each function call can't finish until the final function call finishes. So this generates a stack in memory. In a place, it's called the stack. Stupid name for it. And it's there until completion. So this can occupy up a lot of memory. We're going to start off by taking a look at the isPrime function. So the isPrime function takes in an integer p and checks to see if it's prime. So if I equals p, so if I equals p, return 1, which means it's true. 1 is true and 0 is false. So if that's the case, how is it getting to how does it prove false? It goes through and checks the modulo or the remainder from the modulo division. Does anyone remember what that does? The parenthesis sign between two integers?
It's the.
I mean, it said the name of it.
This operator. It's like if you have 5 divided by 3, it's only going to show 1, or it's going to show 2 because that's.
It's going to show 2. It shows the remainder of division. So modulus operator shows the remainder from division. That's a recap. So it starts with I equals 2 and goes, all right, is our number divisible by 2? If it's divisible by 2, it means it doesn't have a remainder, and so we're going to return false. It's not prime. And then when it goes, okay, well, if that's not the case, both of these are if statements, and neither of them are met, it says return isPrime p I plus 1. So I equals 2 is going to jump up to I equals 3. This is what it's going to look like in memory. And I got a neck. Well, I don't need that. So we've got. Let me just write down the command or the program real quick. Why is it so bright? That's as dim as it gets. Oh, we do that. So the isPrime program, it's a bool program, so it returns a boolean, and it takes in int p. I'm off screen. Int p and int I equals 2. And I'm just writing it so that way we have access to it while we're writing. If I equals p, we are going to return 1, saying that it's true. If p modulo I equals 0, we're going to return 0. Otherwise, we return is prime pi plus 1. Okay, that's the program. Oh. Finish the function. And so let's do something. This is what we're going to do is called the recursive trace. Now, Professor Redden, the other teacher, really loves to go upwards on this. Who fucking writes starting at the bottom of the page? Well, there are languages that do. We're not one of them.
You don't need points for that, because I wrote it, because I wrote it downwards.
So he, in his head, a stack is like a stack of plates, and thus stacks have to go up. But any physical stack is bound by gravity. That's what holds it together. In an actual program, if you've got empty memory, like empty page space, you're probably filling it up at the top and going down. So I'm going to write going downward. He's a big fan of going the other direction, but he's not here. I am. So we have our int main void, and let's have a little call in there. We'll see out, I don't know, is prime. Let's check 7. And we'll take a look at, I don't know, 25. So I'm going to go over and run those real quick and show the results. Let's come down here and do that. Maybe make it read a little bit better. Is 7 prime. Let's see. Is 25 prime. Oop. I guess I have to actually do the damn call, don't I? That really helps. All right, let's see what we got here. 7 is prime and gave return to 1. I should probably do a little bit of coding if I wanted to actually use this. Have it like if true, print out yes it is. If false, no it isn't, but we can see that it's working. So let's take a look at the recursive trace of this. So when we have this bad boy right here, what we're doing is we're sending this to a little box in memory. Memory space is taken up, and we have p is our value here, so p equals 7, and we have I equals 2. And what it's doing is it's checking A and B. I'll call that A and B. So A didn't work, B didn't work, and so it's going to return is prime 7,3. Is prime 7,3 is a function call. So our stack grows. I'm going to make a bigger box because that looks like it's hard to read. In this box, P is 7 and I is 3 now. And it checks A and B. A is no, B is no. And so it returns is prime. Look at this. What's up, dog? I plus 1 is 3 plus 1 is 4. If y'all haven't met Eric, he you went to San Jose, right? Reach Sloan back here. He's like, I didn't learn enough programming. Aren't you data science? Are you hating it? I'll talk to you after class. He came hunting me down. All right, so it's going to return is prime 7.4. Is prime 7.4 is a function call. So it's generating another spot in memory. And it's assigning, we've assigned p equals 7, I equals 4. Only the first time did this int equals 2 take effect. Afterwards, we started assigning I ourselves, and it overrode the 2 that was automatically there. 7 does not equal 4, so it's not returning A. 7 divided by 4 is not 0, so it's not returning B. So it's going to return is prime 7.5. And this is going to go on for a little while. P equals 7, I equals 5. They're taking up integer memory because we've defined them as integers up here. Again, it's not, A doesn't work. It's not divided by 5 evenly. And, or it doesn't equal, they don't equal each other and they don't have a good remainder of 0. So that's going to return is prime 7 and 6 because all we're doing is incrementing I each time. We come down, it makes another stack, or the stack grows. P equals 7, I equals 6. Again, it doesn't work. So P equals, or return is prime 7, 7. So A now works. So we're going to return 1. So we're in our function state here. We're returning 1. It returns it right back up into there. And now that says return 1. Pardon me if I'm writing return as RET, just trying to save a little writing here. And that 1 is coming up here and getting put right there. So now this line says return 1. And you can see this is going to go all the way back up. And as each time it goes back up, this one closes down, then this one closes down. It's deallocating memory as it doesn't need it anymore. So memory deallocates as it is not needed anymore. This one comes up here. This says return 1. So it sends a 1 up here, deallocates the memory. This one sends a 1 up here, deallocates the memory. This one sends the 1 back to the CO. And that's why we got is prime 7, the 1 appeared. And then that one shuts down. Make sense? All right, so it's important to note, and I'm sure you can see, this recursion process can hog memory. Do I have all bad pins in my fucking bag? What is this bullshit? I can really hog the memory. Let's take a look at like, how can we break this shit down? Oop. Can I blow up my memory? Can I blow the stack? That's what Professor Redden likes to say. It's fucking great. So I don't know, let's check. We'll go through the is prime 25 in a second. This is 3 million, I don't know, let's do big number. 1 prime. I think I need another end line right here, or I'm gonna look late. There we go. It's fucking prime too. Or not prime. I thought it would have been prime. Let's go find a prime number. List of large prime numbers. Ugh. More power.
Is there ever a time where we want to have a recursive function? Because I know like it takes a lot more memory and it's usually a lot slower too. But
It's not necessarily a lot slower. Can be. Oh, I don't want to export it as text. I don't know. There we go. 6131. Does that break our shit? You know what? I'm just gonna do X right here. It's mad about something. Blew my stack. That went and got too high. So there are alternatives. When you have it break, when you get an exception, if you're using Visual Studio's, Square will shut it down. So I don't want to do that anymore. Let's kill that line. Anything that we do iteratively or recursively can be done iteratively. And when I say iteratively, I mean like with a for loop or something like that. Can be done as recursion and vice versa. Let's go take a look at the 25. Let's go through its breakdown. So we're going to walk through a recursive trace for 25. This is an old pin, does it work still? So we have is prime 25 in main. And it sends a function over to memory. It sends p equals 25, I equals 2. Of course, I does not equal p, and p mod I does not equal 0. So it's going to return is prime 25 and 3. So we get another window, boom. P is 25, we got more on the stack. Memory's taking up. Again, I doesn't equal P or P doesn't equal I, and P mod I does not equal 0. So we're gonna do return is prime 25 4. And when you're doing these, you start getting into a jam. Like you're like, oh, it starts getting repetitive. Equals 25, I equals 4. Again, that shit holds true. So we will return is prime 25 and 5. Now, P does not equal I, but P mod 5 does equal 0. So this is option B, and option B was return 0. So this is going to return 0. And 0 comes up here, dropped in there. The memory gets deallocated. Pop. This says return 0 now. So it brings a 0 up and it pops off the stack. This now says return 0. So it brings a 0 up here. It pops off the stack. This returns 0. It pops off the stack as it returns 0 to the main. Make sense? All right, is there anything else I want to say on this one before we do a different one? Now, let's take a look at the Fibonacci sequence. So I'm going to comment that stuff out.
You're not showing your screen.
Thank you. Does everyone know the Fibonacci sequence? Or does anyone not know the Fibonacci sequence? Or at least know the premise of it? Let's come over and look at the Fibonacci sequence. So the Fibonacci sequence shitty pen. It starts with 1, the next number is 1. Once you have the first two numbers, it's now I equals I minus 2 plus I minus 1. So the third step, the third number equals the second number plus the first number. The fourth number equals the third number plus the second number. And you're just basically adding the last two numbers to generate the next one. 3, 5, 8, 11, 19, not 11, 13. What am I doing? Scrub over here. 13. I'm a math teacher, can you tell? 8 plus 5 is 11. And so this process keeps going on. The sequence just goes on without end. This program supposedly generates the ith term. And I will write it on the next page because we are of course going to do a recursive trace on it. That's what we're here for, we're learning recursion. So we've got, you know what? It says int Fibonacci, but I think we're going to shorten it down to fib. I'll write Fibonacci for now. Int x. And we are going to shorten this to fib in the actual program. Well, at least in my recursive trace, because writing Fibonacci a bunch of times is a long word. So in this, we have to have a base case. we have to have a case that terminates the program. So the base case, if we're passing in X, and we're going recursively on it, it is if X is less than 2, return X. And then we have our recursion. We are going to return fib x minus 1 plus fib x minus 2. Just like I wrote up here. I use I've got X here as my integer. That's what we'll return, and the function call is over. So like, let's say we pass in, here's our main, and we say fib 7. So this should produce the 7th Fibonacci number. Produces 7th Fibonacci number. So what's going on here? So we take it, it sends over a 7 to the main, or that memory, x equals 7. And it comes over here and it checks out A and B. A, B. So is X less than 2? No. A does not work. So it triggers B. B is return fib 6 plus fib 5. Oh, this may not work very well. This is going to be a lot of paper, right? This should be a branching tree that just keeps getting bigger and bigger. We're going to be lazy fucks though. So what I mean by lazy fucks is exactly what it says. I'm going to do the bare minimum here as writing it. Just remember, like on and off, I'll sketch a tree real quick after this. We'll do our fib 6 over here. And we'll do our fib 5 right here. In neither case is X less than 2. So this one is going to return fib 5 plus fib 4. And this one is going to return fib 4 plus fib 3. Okay, so technically what I should be doing is generating a new fib 5, but I'm not going to do that to save some paper. I'm just going to point over there. It's technically doing a new one. Just keep in mind that's how it eats up memory so fast on this. And it's got to generate a fib 4. We'll do fib 4 down here. And this one needs a fib 4, and rather than making a new fib 4 for it, I'm going to point over there, and we will point to fib 3 right here. All right. So X equals 4, neither of these is less than 2. We're checking our things, A or B. Neither is less than 2, so it's B on both of them. This one is going to return fib 3 plus fib 2. So fib 3, again, I'm not going to reinvent the wheel. I don't want to like take up a whole lot. I can use the whole damn board to sketch this tree. It would be a big sketch. And it's gonna make, it also needs x equals 2. X equals 3 is gonna return fib 2 plus fib 1. So fib 2 points over, well, it points to its own one, but again, we're being lazy fucks because that's how we roll, or at least that's how I roll. Now we check. X equals 2 does not meet A. So this one is going to return fib 0 or fib 1 plus fib 0. So we got another box down here for x equals 0. And it points to this one and that one. I guess I could have just done like that, like I did everywhere else. All right, so x equals 1. X is now less than 2, so it returns x. Returns x, which is return 1. So this one is going to send a 1 back here. And it's going to send a 1 back there. So I'll put a 1 and a 1. Let's start, and that'll collapse x equals 1. This meets the x is less than 2. X equals 0 is less than 2. So it's going to return 0. And that sends a 0 back up here. So it puts a 0 there. And this one shuts down. Okay, so both of these need fib 2. Fib 2 has 2 numbers. It's got 1 and 0. So this is going to return 1 plus 0. 1 plus 0 is 1. So this one is going to return a 1. And it's going to return a 1 there. So fib 2 is 1. Fib 2 is 1. That one shuts down. It's completed its call. Fib 2 plus fib 1 now has 2 numbers. It's 1 plus 1, which equals 2. So this is going to return a 2 up here to fib 3. And it's going to return a 2 over here to fib 3 over here. So this has got 2 plus 1 equals 3. This one sends, this is Fibonacci 4, x equals 4. So Fibonacci 4 is 3. It passes the 3 up. And it passes the 3 that direction also. So this one's going to shut down. And the 3 is right here. 3 plus 2 is 5. So the 5th Fibonacci is 5. It's going to send that back up here to fib 5 right here. And it's going to send it over here to fib 5 over here. It's going to shut that box down now as the memory deallocates. A little repetitive, right? This is 5 plus 3 equals 8. That returns to fib 5 up there. Or fib 6. Fib 6. Fib 6 is 8. 8 plus 5 is 13. It passes 13 back up to the main. And the memory has now been entirely deallocated, and we got our answer in the main. Now, was that correct? Was our Fibonacci sequence? Our 7th number was 1, 2, 3, 4, 5, 6, 7. Was our Fibonacci 6 8? Yes, it was. Was Fibonacci 5 5? Yes, it was. And we can see it's producing all the numbers of the Fibonacci sequence as it goes. This bad boy literally though is making a damn tree. You know, it's doing stuff like that. I was cheating and pointing a bunch of arrows. This one is quickly making a lot of things on the stack. This one's got 2, these generate 2 each, these generate 2 each, and so on and so forth. And we went 1, 2, 3, 4, 5, 6, 7, 8 layers. So this tree is gonna have like 5 more branches, 6 more branches. It's a lot of paper writing. Let's go take a look at it in the program. Now, I wrote what it looks like it's reading as, but let's make sure. Did I just flat out delete it? I did.
It's like off.
That's because I keep hitting PC rather than laptop. Thanks for the warning. See out. What is the 7th Fibonacci number? And we'll do Fibonacci 7. So Fibonacci number is 13. All right, so your first assignment, we're gonna go take a look at it real quick. Is it here? There we go. That's not your first assignment. Is to do some recursion tracing. One of them is sum up to. It starts with int sum equals 0. Let's see this. So you'll have that. You can do practice recursive tracing. What this is doing is it's adding the first n numbers. So you should be able to do that and know what the actual number is relatively quickly by hand. You had to have made it through some math courses to get to here. There's even a cheat formula for how to add up if you go for a big number. The second one, the binary search, searches an array for a value. So A is you send in the array first, you send in the starting index and the ending index, first and last index, and then you send in the target number it's looking for. Okay, so we have int mid equals first plus last minus first. This is integer division and it's correct. We don't want to have a double here because we're looking for indices. So here it calculates what is the middle of the array and then says, is the target equal to the middle of the array? If so, return it. Return the index and say this is where we found the target at. After that it goes, okay, well, if the target was not, because notice it needs to be in numerical order. If the target is not if the target is less than the value at the midpoint, do first to one of the midpoint less 1. So the index shortened 1. And if it's not, if it's greater than the value at the midpoint, then do the last half. This is almost like finding roots by hand. Just plugging numbers and trying to find out which region it's in. Try to work this out, do a recursive trace on this. Let's see, there's 9 elements. So the first one, midpoint's gonna be 15. And then it'll shorten down to 7 and it should shorten down to 6. So it shouldn't take you too many steps to do this one. Ooh, that's big. Then you were gonna modify the code that was in that last thing, the binary search, to do strings, try it with strings. Recursive pi. Finding pi through recursion is a pain in the ass, so I'm gonna get you started. Okay, so this is actually kind of interesting. Pi equals, if you go to enough steps, you can do 4 times, look what's going on. We got 1, this is effectively like 1/1, then this is -1/3, plus 1/5, -1/7, plus 1/9, so on and so forth. So I recommend that we don't jump to that right away. Why don't we get started off with doing the sum thing first? And going from there. Let's see, I'm gonna go copy this and put that in the program now. And then we'll come over here and look at what I'm talking about real quick. So this might be a little hard as it is, so maybe we should think about how we would do the sum first. So let's do the sum of up to like the first 4 numbers. So we should end up having 1 + 2 + 3 + 4 = 10, right? And let's say we're passing the number of terms we want in, like, so let's say we're doing sum and we pass in like int x, where x = 4. So we're telling it to find sum 4. So let's draw the boxes. We don't know what they're doing yet. Let's draw the boxes and kind of figure out what our formula is going to be. X = 4. Then we go down to x = 3, x = 2, and x = 1. So, and we don't want it to go past 1, so maybe we'll call the base case 1. Base case, if x = 1. Maybe we'll return x, or return 1. Seems reasonable. So that's going to bring up here and it's going to do a 1. And we wanted to add it to whatever's here, so we're going to do 1 + 2. 1 + 2 should return a 3. And we would have a 3 here. And we want to add that 3 to it. 3 + 3 is 6. So we got a 6. And we want to add the 4 to it, so we return the 10. So what do we got to make this return called for everything else? Well, this one was this one right here, right? So this is like, if I'm at x = 2, I'm going to return sum of x - 1. Does that seem like it's going to work?
Yeah.
And then I'm adding into it the current x. Does that track? Does that seem like it makes sense to everybody? You're the SI one.
Well, I'm just.
We better make sense to you. Like, I want to make sure everyone else is on board. Let's go take a look at, let's code this up. So let me comment out my favorite. Okay, good, I got the right one shown. I'm being lazy right now, I'm not doing separation. You guys wanna do separation? We're having it, let's say in some recursive. And we're passing in integer x. And we said our base case was if x equals 1, return 1. And then otherwise return some recursive x minus 1 plus x. I'll come down here, I'll be like, okay, let's say n equals 4. See out sum of the first 4 are first. Numbers is, we're gonna do some recursive n. That way I can edit it easier and still make it make sense. So here we're doing that one, let's put a little space in there. The sum of the first 4 numbers is 10. If we added another number, we're adding a 5 to it, the next number should be 15. We want to test it for a few numbers. If I add a 6 to it, it should be 21. So let's try checking 6. Don't just ever test one case, you want to test a couple. So it looks like the sum thing is working. Now let's go back and look at the pi thing. The pi is doing, though, it's not doing the sum, it's alternating. We'll address alternating last. Alternating is actually not too bad, but there are odd numbers on bottom. So we want to do, like, let's say we're just going to add odd numbers together. So let's try adding odd numbers. Say sum odd. And I'm going to pass in an integer x. Let's say this is represents the first x odd numbers. First x odd numbers. So we're gonna do this over here. It sends it over. We've got x equals, let's start with x equals 4 again. X equals 4, we're gonna have x equals 3. That looks like a lambda. X equals 2. X equals 1. Okay. So what are these odd numbers? Let's write down what the odd numbers are over here. The first odd number is 1, the second odd number is 3, the third odd number is 5, the fourth odd number is 7. Those are our targets. This one should be returning 1. So we'll make that our base case. If x equals 1, this works better if we use different colors for the actual text and green for the common outline. If x equals 1, return 1. And then we got to figure out what we're going to return otherwise. This gets a 1, and I want to add to it a 3, so it should return a 4. So what we need to figure out is how do we map, so we put in x, this is like x, f of x. If I put in 2, I need to get out a 3. Here, I need to put in a 3 and get out a 5. Here, I need to put in a 4 and get out a 7. It looks like there would be put in a 5 and get out a 9. So the formula that works for this is 2x minus 1. Okay? Hopefully, I think you've all had to have taken calculus 1 by now. That had to have shown up somewhere in there, right? It's got to show up there in somewhere. So we wanted to, well, first off, I wanted to return the sum of the one below it. So we want to do return sum odd x minus 1. And then we want to add to it the current x going through this process. So 2 times x minus 1. Is that working? Let's check it. If I stick in x equals 2, does this process work? I'm getting sum odd, when x equals 2, I have sum odd 1 plus 2 times 2 minus 1. This one is a 1. This is plus 4 minus 3. 4 minus 1, sorry. I'm getting 1 plus 3. That is what I'm getting. We can check the next few, but x equals 3, x equals 4 should do the same thing. So as this is going up, it's adding the last sum plus 2 times the current x minus 1. 2 times 3 is 6 minus 1 is 5. That checks. And so this is doing 4 plus 5. It's going to return 9. And here we've got 9 here. It's going to do plus 2 times x, which is 4 minus 1. This is 8 minus 1, which is 7. That works. 9 plus 7 should return 16. Interestingly enough, what are these numbers here that each one going up is returning? 1, 4, 9, 16. They're the perfect squares, right? I wonder if they're all like that. We'll check it. Seems like it though, right? The first 4 are returning squares. Let's come over and code this up. Sometimes it takes a little work to figure out what that function is. And rather than have you guys all go look up shit on Geek for Geeks, I'd rather you work you through the thought process on how to do some stuff. Hopefully you've seen the 2n minus 1 or 2a. It's often taught as 2n minus 1 because they use n in the formulas. So we had the sum recursive. Let's do some odd. Is there anything else I want to say with this? Nope. We'll call it odd rec. And I had, it was pretty close to this. Return some odd. And we wanted 2 times that minus 1. What am I doing? Let's do this. Some of the first odd blank numbers is some odd rec. And we did 4 on paper, so I want to make sure the 4 works. some of the first four odd numbers is 16. Does n equals 5 goes to 25 like I think it's gonna do? Let me comment out that one. 25. Check 6. It's actually giving us n squared, right? Or x squared? Not just any square number, but the actual one we started with squared. So by that pattern, I should be able to throw in 100 and get 100 times 100 is 10,000. I don't know if it's gonna crash it or not though. No, good, didn't crash. This isn't as bad as the Fibonacci one because it's only making one box at a time and it's only storing one variable at a time too. So it's a little bit nicer on memory. But that's not what we were looking for. So we're looking for pi. We've got odd numbers right now. Let's come over and now like look at what we're aiming for. We've got a formula for odd. We're going to use that 2n minus 1 pattern here. The pi though, pi was 4 times 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11 plus 1/13 and then a minus and it just keeps going. So the 4 multiplier is going to be piss you off. Just distribute it. Pi equals 4 over, I'm going to treat them all as fractions. 4 over 1 plus 4/3. Sorry, not plus 4/3, but minus 4/3 plus 4/5 minus 4/7 plus 4/9 minus 4/11 plus 4/13 and onward. Now, this might be easier to make sure it works for, do the alternating last. Let's alternating bit last. Let's try just doing adding them all. So we'll call this pi recursive. And we're going to start off with int x equals 4 again. And so this means we want to have a box over here that starts off with 4, goes down to 3, x equals 2, x equals 1, and stops there. So what is the first term in our sequence? 4. So we want this to return a 4. That's going to be our base case. And pi is a decimal answer, so maybe we're going to say 4.0. So our pi recursive should be a double pi recursive. And it can take in an integer, which is fine. So this is going to return a 4. And right now, before we do the alternating, right now we wanted to add 4/3. But the bottom is the odd thing. So 4 plus 4/3 is, I don't know, I don't want to work it out. 12 over 16 over 3, 5.3333, that seems fucking high. But we're adding, that's why.
No.
And so this one is going to return that answer up there, and we wanted to add 4 over 5 at this point. And we want this one to add 4/7 until we fix it. So our base case is just return 4.0. If x equals 1, return 4.0. And then otherwise, we are going to return, let's take a look at what we're going to return. We want to do the pi recursive x minus 1. We want to get the 1 below it. And then what we're adding to it is plus 4. Again, I'm going to say 4.0 to make sure it does everything as a double. And then we're dividing it by, this is where you have our odd function. 2 times x minus 1. I'll put that in parentheses. That's a big parentheses. Does that make sense? Will that work for each one? 4 over 2x times 1? Or 2x minus 1? When x equals 3, I've got 6 minus 1 on bottom is 5. That works. When x equals 4, I got 2 times 4 is 8, minus 1 is 7 on bottom. This looks like that might work. So we're going to do the previous pi plus 4 minus it. Let's go over and code that up. We wanted this one to be a double. Pi recursive into x. And I'm going to go hijack this shit, speed it up. X equals 1, it was return 4.0. And here it's return pi recursive. And this should be 4.0 divided by parentheses. So we got our current value, and then add 4.0 divided by 2x minus 1. So come on down here and test it. I'm not going to make a statement. Let's just do it. Pi recursive 4. And then let's make sure we check a couple. Let's do pi recursive 5. Pi recursive 6. Put some end lines in there, Jones. That's not even readable. All right. I'm not going to assume it's work, so let's try to get out of the calculator and add this shit up. So I got 4 plus 4 divided by 3, oops, plus 4 divided by 3, plus 4 divided by 5, plus 4 divided by 7, and I'm getting 6.704761905. The first 4 worked. I'm going to add 4 divided by 9. 7.149206. 06 rounds up to 1. That's working. I'll add 4 over 11. 7.512842713. This looks like it's working. All right, so far our code is working. We just haven't compensated
Shouldn't it be the more term, because we're trying to find pi, right? So shouldn't the more terms you go, it should be getting closer to pi, not farther?
We don't have the
Oh,
minus
we're
thing
only
yet.
adding, right?
Yeah, we need to get that, we need to get the subtraction in. So let's go back to the paper and figure out what we're doing here for subtraction. Because we've got a couple choices. The first choice we've got, let's see, let's number our terms here. So when n equals 1, 2, 3, 4, 5, 6, our term is, we've got 4 over 1 here, we've got minus 4 over 3 here, we've got plus 4 over 5 here, minus 4 over 7 here, plus 4 over 9, minus 4 over 11. Oops. Now, one way we could do it, we could definitely just say, it looks like the odd terms are when n is even, right? Or that, not odd terms, the negative terms are when n is even. Did everyone see that? So we could do if n mod 2 equals 0. We're gonna find out that that's not the best choice later on. If statements are not that efficient. We want to, there are more, you're better off doing mathematical operations which are more efficient than doing if statements. We'll see that when we're gonna time shit later on. We're gonna code shit that does like 100,000, a million operations, and you're gonna time it based on how many ifs and shit you have in there to figure out like how much it slows it down. That's later on in the course. We're doing it. We're gonna do it. It's fucking cool. So this is not desirable. So a better choice would be to use -1 to an exponent. But let's check out what -1 to an exponent does. If I have -1 to the n right here, let's make another column for -1 to the n. And we can multiply it by our 4.0 divided by the 2x minus 1. We just multiply it by that because -1 alternates. So -1 to the first power is negative, and -1 to the second power is positive. Oops. And so it looks like we're off by 1. So we don't want to do n, we want to do -1 to the n plus 1. Okay? So, does that make sense to everybody? How to get the alternating in there? So if we want to use CMath for the POW function, not int, include. So I'm including CMath, and we're going to say plus POW -1, comma, and we're doing it to the x plus 1 times 4.0. So that should get us our alternating bit right there. And we have it times the 4.0, so it looks good. How does, oh, why did I undo these? Let's take a look at what the 4, 5, and 6 give us. Nothing that looks anywhere near like fucking pi. Right? That doesn't look like pi. That doesn't mean it's not working. Our formula worked. Just finding pi with this shitty ass approach is not that effective. So yeah, comment those out. See out pi after n terms with the formula is pi recursive n. So after 100 terms, what's it look like? 3.13. Maybe let's make it 200. Still 3.13. Ah, fuck it, 500. Still not 3.14, but it rounds to 3.14. Thousand. Hopefully it doesn't break. Well, we're getting closer. We got into 2 decimal places now. But it's, the 59 is misleading. It's 3.14159, right? So our 3rd decimal place is on. Let's check maybe doing 2000. If it breaks my computer, I'll know to stop. 2000 got me to 3 decimal places. Maybe 4,000. No. It's shit on my parade. All right, let's try 3,000. We're getting there. So that's how you can code up pi. I am not going to put the pi code on there because it's one of your labs, and so I want you. But if you've been following along and typing shit up, you're good. Let's go back and look at all of these as an iterative approach. We got several formulas here. I'd like to take a look at doing these iteratively. Well, we can start with our pi. That's the one that's most recent in our head, right? So what kind of for loop do we need? For int x equals 1 x, fucking bad, I less than n, I plus plus, here we go. Put that above it, and then we can check them both at the same time. Just lower that back down to a smaller number. So it needs to add 4 plus, it needs to kind of like follow this recursive formula. Because like even when x is 1, this works. If I just change that to I. And I want to give it a little value here real quick. So int temp, not int, double temp. And we'll call that temp equals. But we wanted to keep adding it to the previous one. So we got to do temp equals temp plus that, which means we should initialize it at 0. And then I will do CO temp. Pi after n terms with the formula iteratively. We'll make that say recursively. And this will be temp. And this is something. I got 2 CLs, what the? They're like, sure, bud, whatever you say. Do we get the same thing? Yeah, we do. So let's go take this and put this,
Would you be able to put more terms in it, or would it be the same amount of terms before breaks?
that's a good question. So 4,000 broke it, right? There's no reason, 4,000 broke the recursive.
Yeah.
There's no reason for this to break the for loop. Because it's not building a big stack, it just keeps replacing the same number over and over and over. I should be able to do 10,000 here. I was able to do 10,000 terms.
It's still off.
It's still off. So it's not the best formula, right?
Not really.
So the iterative approach will go farther. The iterative approach is not bound by memory. I'm gonna come up here and like make this a little, I never finished the damn, or did I? Yeah, there I did. I wanna put an end there and we'll make a new one. Double pi it. Double temp equals 0. And for int I is less than x, there we go. And so I can come down here and get rid of this bit right here and say it's pi iterative. Turn that one back on. Nope, I fucked up something. What did I fuck up? The iterative worked. Did I screw up the recursive formula?
Did you have a return in your iterative?
No, I don't. Told you, fucking overachiever. He's over here doing his own shit and still correcting my teacher shit. Are you sure? So we've got pi recursive, pi iterative. You'll find, notice like a lot of these was just using the same shit. So we could do this iteratively as well. Sum odd iteratively. And you'll start off with some temp value. And then you're gonna do a loop. Why not just copy the loop? Save yourself some steps, Jones. And we're gonna replace this up here. Theoretically, it looked like all I had to do is drop this part in from the recursive into the iterative. Let's try that on the sum iterative. Sum odd iterative, and I want to return temp again. All right, let's turn off the pi while we're playing around. And we're looking at the sum ones. So, see out first. Odd terms added together iteratively equal sum odd it n, and we'll have it do the recursive. this is some odd rec, yeah. Oh. Let's do n equals 100. Who is the kid that got in trouble? His famous mathematician.
I don't remember, but I know the story, I know his equations.
Yeah. He's in class, he's a little fucking kid, the teacher says add up the first 100 numbers,
Oh, I see.
and he fucking spits it out, like gives the answer in like just a few seconds, and he fucking gets the ruler for it. They think he's fucking cheating. This should be, I believe this one's 5150. It's you add the first and the last, and then you multiply by n over 2. So 101 times 50 should be 5050, not 5150. 5150, that's the crazy code, right? Let's take a look, 5050. Take a break something. That's 20 seconds, something's broke. All right, let's come up here and look at some odd iterative. That's what I don't need.
Oh, yeah.
That's what's off. I copied and pasted some shit I didn't need. Neither of them are right. What happened? Didn't this shit work just a second ago? Oh, these are odd terms. I don't know what the first n odd terms are. But they should be equal. Those weren't equal. So the recursive one was the one that worked. I know it worked. So what's going on with my sum odd iterative? When x equal, I'm using x. That should be I. It wasn't changing. There we go. That's neat. The first 100 odd terms add up to, oh yeah, because it was n squared. Duh. But notice, all we had to do is basically strip the recursive part of the part that, just get rid of the part where it calls itself again. And for the for loop, you're doing, just adding that again with it, you have a temp value and return the temp. Any questions? I'll post all of the stuff except the pi part. I'll post the sum odd iterative and the sum odd recursive. That way you guys don't have to remember that shit, but pi one. Now, if you want to be a real badass, bonus for using your own power function, see lab 2D. What's your lab 2D? Write your own power function that calculates powers of x to the n. Don't use the math library, don't use POW, don't use CMath. You try working it out iteratively, try working it out. It's easy, maybe easier to start iteratively, I don't know. I was starting recursively and going backwards, but try whichever way you want to try first. We saw that going between the two isn't a big difference. The actual repetitive part, both in the for loop and in the recursion, was the same. So once you've got it figured out, whichever way makes it nice and pretty for you, do that. And then you can go back and edit your lab 2C, get rid of CMath, and instead of doing POW here, put in like POW Joseph. Bam.
Yeah, because it'd be a function.
Pow Hefe. Hefe power. Hefe power. Now, this is on pow. Right? Boswell, like the next lab, maybe I should change the order of the labs. No, I'm sure now that I've opened it up today, Amitech is already done. You're fucking machine. He's a machine. I'm pretty sure you're the only one that has all of the first chapter labs done. I didn't scroll down and look at the list. I knew you had them all done though, right?
Yeah.
Does anyone else have all the first chapter labs done? No, this is the guy. This is the guy that you want to go, hey, I need to pick your brain. Don't give him your code. Just give him ideas. Don't give him your code. Make him work for it. I think that's all I got for you. Unless you guys got any questions? Oh shit, they're all fucking doing all sorts of shit.
Forgot about the other students.
What just happened? Ah! I yanked my cord up. No, we're not. I don't even know what I was saying, Ainsley, so what's that to? What did I just say? Oh, she's probably talking about being done with all the labs like Amitesh's. Nobody's doing it. You've been working on your labs, don't lie. You've been submitting them. All right, if you don't have any questions, have a good evening. I will be here tomorrow. Yeah, the basic key wasn't ready for me. Get this, this fucking blew my mind. Because I went over to the police station, the COS police station, to grab a key for the Mason Center. I checked one out, went over there to get it. They said they didn't have the key yet, that it was on order because they opened up the new building where the math lab moved over to. And apparently they need so many fucking keys that their key place ran out of fucking keys. Holy shit, that's a lot of blank keys. How do you run out of fucking keys? And you're a key place. That's like going over to Tahoe Joe's and they don't have any fucking potatoes or steak. What the fuck? So, I'm gonna be in John Muir 101 tomorrow from 9 a.m. to noon, which is right next door. I'll be in there. If anyone's interested in coming. Other than that, get the fuck out.
What?
Just tutoring.
Oh.
They're paying me for it now, Eric.
Really?
I don't have to do it at Starbucks anymore.
Oh, really?
Yeah, I get paid for it.
Is it every day or what day?
It's not a fuck every day. What the fuck? It's on Saturday.
It's on Saturday.
God damn, I want to have some sort of a life. It's right downstairs.
Wow.
How you been?
All right. Go to a Java class and find out the teacher is writing C++ code.
Wait, what?